Yo, what is up YouTube? In this video I wanted to talk about a problem that was on my engineering electromagnetics problem set. This was homework 3, I believe. We talk about Gauss's law. So how are we going to apply Gauss's law on this problem? Let's go ahead and read it. It says it's a spherical shell with outer radius b. It surrounds a charge-free cavity of radius a, which is less than b. So it shows the figure there. And the shell contains charge density given by rho v equals negative rho v naught over r squared for a less than or equal to r less than or equal to b. So r is between a and b, inclusive, and rho v naught is a positive constant. And then we have determine the electric flux density d in all of the regions. So let's go ahead and write out what Gauss's law says. Gauss's law says that the surface integral of d dotted with ds is equal to the charge enclosed. The charge enclosed is the charge enclosed by the Gaussian surface that we draw. So if we want to find what the electric flux density is at each of these regions, we can draw like a Gaussian surface for those regions. So for r less than a, we draw a sphere. It's going to be inside of here, and it's going to have radius r. And r is going to be less than a. So let's go ahead and say for r less than a, we have the surface integral of d dotted with ds is equal to q enclosed. And from the problem, we're given that there's a charge-free cavity of radius a. So everything that has radius a or less is going to have zero charge enclosed. So since q enclosed goes to 0, then we know d has to also go to 0. So for r less than a, we know that d is equal to 0. Okay. And now let's look at a more interesting region where we enclose a little bit of charge. So let's look at for r between a and b, we have the surface integral of d dotted with ds is equal to q enclosed. And when we solve for q enclosed, we find the volume integration of the volume. So the charge density, which is given as a volume here, integrated over that volume. So that's going to be equal to, it's going to be a triple integral in spherical coordinates. We're going to go from a, because that's where the charge starts, and we're going to go to some arbitrary radius r, which is going to be less than b and greater than a. And we plug in rho v, which is negative rho v naught over r squared. We're going to have a couple more integration bounds here. It's a full sphere excluding the center, so we go a to r, but we also need to go with the azimuthal angle theta equals 0 to pi, and then the other angle is phi equals 0 to 2 pi, and we need our integration dv, and we know dv equals r squared sine theta d theta, or it's going to be d phi d theta dr. So we'll throw that in there. R squared sine theta d phi d theta dr. And so this integration can be broken up a little bit. These r's are going to cancel. We can take this constant out and we get negative rho v naught multiplied by the integration a to r of dr multiplied by the integration 0 to pi of sine theta d theta multiplied by the integral of 0 to 2 pi of d phi. So this we get r minus a. Over here we get negative cosine evaluated from 0 to pi. So that's going to be equal to negative cos of pi plus cos of 0, which is equal to negative times negative 1. So positive 1 plus cos of 0 is 1 plus 1. So this is equal to 2. Over here we get phi from 0 to 2 pi, which is just 2 pi. So this times this gets us 4 pi. And so in total, Q enclosed is equal to 4 pi, negative 4 pi rho v naught times r minus a. Okay, so we have the right side of the equation solved for. Now let's talk about the surface integral over here, d dotted with ds. Something we know about this because our charge density is only dependent on r. We know that our electric field is going to be pointing radially outwards, so we're going to have some good symmetry there. So let's go ahead and draw out our Gaussian surface. It's going to be a sphere with radius r, and now again we're doing r less than greater than a but less than b. So it's a surface integral, and we have, let's say, some ds, some d coming out of this. How is that d related to the surface area? We have some differential surface area, and the area vector goes in the same direction as d. So we can say, we can represent d as some magnitude dr times r hat. It's all of d is pointing radially outwards based on the symmetry of the problem and the charge density. We know that the flux is going to point outwards, and that's going to be in the same direction as ds. We know ds is also going to be r hat. And if we take a differential volume, a differential surface area on a sphere, it's equal to r squared sine theta d theta d phi. So ds is r hat times r squared sine theta d phi. So if we replace this in the integration, we get a double integral. We're going to go from 0 to pi and 0 to 2 pi of dr r hat dotted with r hat r squared sine theta d phi d theta. And I'm just switching these so these match up with the bounds. So since it's r hats dot product together, the magnitude is going to just, we'll just be left with the magnitude. This r dot r is going to be equal to 1. So we're left with integration 0 to pi, integration 0 to 2 pi of dr times r squared sine theta d phi d theta. Since these two don't depend on phi or theta, we can get dr times r squared times integration 0 to pi of sine theta d theta times the integration from 0 to 2 pi of d phi. So we did this integration already. This is 2. This is 2 pi. So we get 4 pi r squared and dr. And something you'll notice here, that's just the surface area of a sphere with radius r, surface area. So now we have dr times 4 pi r squared is equal to the q enclosed, which we found over here, negative 4 pi rho v naught times r minus a. We'll isolate for dr. dr is equal to negative 4 pi rho v naught times r minus a divided by 4 pi r squared. These 4 pi's will cancel. We get dr is equal to negative rho v naught times r minus a over r squared. So we could say that d is equal to r hat vector, because this was the magnitude of d, and we know d only points in the r hat direction. So we get negative r hat squared, or negative r hat times rho v naught times r minus a over r squared. So this is for the region r greater than a less than b. Sweet. So that covers the next region. Now, what about if we choose R greater than B? So if R is greater than B, then we can repeat a lot of the steps we just did, but the charge enclosed is going to change a little bit. So on the left-hand side, we'll have dr times 4 pi r squared, where r is some arbitrary r. And then we have the integration. It's going to be a volume integral. So the volume integral of rho v dv. But we're going to have different bounds here because we're talking about what charge gets enclosed. And once you go beyond B, the charge enclosed doesn't get bigger. It just goes, the charge enclosed is only from this region. So you can stop at B. So this is going to be equal to the integral a to b times the integral 0 to 2 pi times the integral 0 to pi of negative rho v naught over r squared times r squared sine theta d theta d phi dr. So we get these r's cancel. We can bring this guy out front because it's a constant. So we get negative rho v naught times the integral a to b of dr times the integral 0 to 2 pi of d phi times the integral 0 to pi of sine theta d theta. So this equals negative rho v naught multiplied by b minus a multiplied by 2 pi multiplied by 2. So we get dr 4 pi r squared is equal to negative rho v naught times b minus a multiplied by 4 pi. If we isolate for dr, it's equal to negative rho v naught over multiplied by b minus a, and the 4 pi's are going to cancel, and we're going to be left with r squared on the bottom. So d for r greater than b is equal to negative rho v naught times b minus a over r squared. Made a little mistake here in the video, so I gave d, the vector, as only in a magnitude, but we have a direction as well. So d is actually going to be equal to r hat multiplied by this thing here. So we get d is equal to negative r hat rho v naught times b minus a all over r squared. Remember, vectors have magnitude and direction. Sweet.